let's just jump right into it. Welcome to today's Explainer, where we are going to unpack the twin hidden superpowers of electric current that literally power our modern world. If you're following along, we're diving into Chapter 4 of the Class 8 Science curriculum, specifically covering all the core concepts up to page 54. We're going to explore two major fascinating things that happen when electricity flows through a wire: how it creates magnets and how it creates heat. Picture this: you're at a school science fair, buzzing with energy, just like students Mohini and Akarsh. They're wandering around, checking out the exhibits, when they stumble upon a working model of a lifting crane set up by a senior student named Sumana. But here's the crazy part. This crane is picking up heavy iron paper clips using nothing but a wire and a battery. There is absolutely no regular permanent magnet in sight. None. So to figure out how this magnetless crane actually works, our explainer is broken down into 6 quick parts: the electromagnet mystery, current meets magnetic fields, building temporary magnets, Earth as a giant magnet, the heating effect, and finally, everyday electrical superpowers. Okay, kicking things off with Section 1, the electromagnet mystery. You know, Mohini was totally, understandably confused by this setup. I mean, we all learned early on that standard magnets attract iron, right? But here, Sumana literally just closed a switch on a circuit, and suddenly a plain old iron nail started acting exactly like a magnet, scooping up all these clips. And the second she opened the circuit, boom, the clips just dropped. It's a massive why that we're going to solve right now. How exactly does a simple, everyday circuit transform into a magnet? Let's dig into that in Section 2, current meets magnetic fields. We can actually see this invisible force at work by recreating a really famous experiment right on a tabletop. Following the steps for Activity 4.1 from the text, it's super simple. You take a piece of cardboard, stretch a wire across it, hook it up to a cell and a switch, and then, here's the secret sauce: you slide a small magnetic compass right underneath that wire. Now, when you actually test this out, the results are wild. When the switch is closed and the current is actively flowing, that little compass needle suddenly deflects away from its normal resting spot. But flip the switch open so the current stops, the needle snaps right back to pointing straight. The compass needle only deflects when the electricity is flowing. So the big takeaway here is that the electric current itself is what's generating a temporary magnetic field. We formally call this the magnetic effect of electric current. Think of it like this: the wire isn't just a pipe carrying electricity. It's literally projecting an invisible magnetic force field all around itself, but only for the exact amount of time the power is on. And if you tried that compass trick, you actually just recreated a massive historical breakthrough. Back in 1820, a brilliant Danish professor named Hans Christian Ørsted supposedly noticed a compass needle twitching during a simple classroom demo. That was the aha moment where humanity first realized electricity and magnetism are linked. Up until then, everyone thought they were just two completely unrelated things. Which brings us nicely to Section 3, building temporary magnets. Activity 4.3 shows us step-by-step how to build the exact same device Sumana used for her crane. It's DIY science at its best. You grab an iron nail, take a long piece of insulated wire, and wrap it super tightly around the nail to make a coil. Hook those ends up to an electric cell, bring it close to some paper clips, and bam, you've got yourself a working magnet. So let's give our crane's secret weapon its proper, formal name: the electromagnet. It is simply a current-carrying coil behaving as a magnet. We use an iron nail inside that coil because the iron core acts like an amplifier, making the magnetic field way stronger. And again, the coolest part? It completely loses its magnetic superpower the millisecond you break the circuit. Now, what makes electromagnets so incredibly useful, especially compared to those permanent magnets stuck to your fridge, is that they're totally customizable. Need it to be stronger? Just crank up the electric current, or wrap a bunch more wire around that iron core. Need to swap the north and south poles? No problem. Just reverse the direction the current is flowing from the battery. It's that easy. Let's zoom out for Section 4, Earth as a giant magnet. This whole concept isn't just for tabletop experiments, it applies on a planetary scale. Have you ever wondered why a compass always points north? It's because Earth itself is basically a giant electromagnet. Deep, deep underground, churning liquid iron in the Earth's core creates these massive electrical currents. And those currents generate the enormous magnetic field that guides migratory birds and literally shields our entire planet from dangerous space radiation. Okay, so we've officially solved the magnetic mystery of the science fair crane. But that naturally leads us to ask about electricity's other hidden superpower. We know an invisible magnetic field forms around the outside of the wire, but what exactly is happening to the wire itself? Does all that flowing current make the wire hot? Let's test it. Moving on to Section 5, the heating effect. Activity 4.5 gives us a great way to safely check this. We take a very specific thin 0.3 millimeter wire, called a nichrome wire, and string it between two nails in our circuit. If you leave the switch on for just about 30 seconds, and then carefully hover your hand near it, you'll feel a very real physical change. That wire gets noticeably, distinctly warm. This warming phenomenon is what we call the heating effect of electric current. But why is it happening? Well, no conductor is perfect. When electricity tries to flow through a wire, it faces pushback. It's kind of like trying to sprint through waist-deep water. This pushback is called resistance. And to force its way through that resistance, some of the electrical energy is sacrificed and converted directly into heat energy, which warms up the wire. You might be asking, why did we specifically use nichrome wire for that test, rather than the standard copper wire that's plugged into all our devices? It all comes down to that resistance. Nichrome naturally puts up a much higher resistance to the electric current. That means a huge amount of electrical energy is forced to convert into heat. Copper, though, it has super low resistance, making it perfect for safely carrying power through the walls of your house without, burning them down. And finally, Section 6, everyday electrical superpowers. Once you understand this heating effect, you start seeing it everywhere. Every single time you switch on an appliance with a glowing red element, like when you're boiling water in an electric kettle, ironing a shirt, or blasting your hairdryer, you're using this exact science. They all have a high-resistance coil intentionally designed to get blazing hot. And it scales up too. Giant industrial furnaces use this very same electrical resistance to literally melt tons of solid scrap steel. So, we've uncovered how electricity generates both invisible, powerful magnetic fields and intense everyday heat. I want to leave you with a thought to chew on based on today's text. Given everything we've just uncovered about electrical resistance and the heating effect, how might relying on electrical appliances be a smarter, more impactful choice for our future than traditional methods like burning wood or coal? Think about the precision, the cleanliness, and the sheer science behind flipping a switch. Thanks so much for joining me on this explainer, and definitely keep questioning how the world around you works.